Yeah, let me. If I remember, actually, the last lecture, if I remember right, then I had a sort of an object like that, and then I said secular approximation. Yeah. And then I had some expression here, and I didn't explain any of this. So to explain that, I think maybe could take a step back and then essentially develop the theory in a rather general way. Actually, there's another subject which I think I didn't cover, which maybe should be covered. If I remember, when I did the first lecture, I wrote down spin Hamiltonians using Cartesian tensors. So if you remember, I was writing down, if I remember, I was writing down the spin Hamiltonian for the interaction between two spins. And the way I did it was to write down the dipole-dipole coupling between the two spins. And I wrote it in this way, actually. Where we can think of this actually as the product of a row vector, which is ijx, ijy, ijz. And then the Cartesian tensor, which is a matrix with 9 elements to it. And then column vector. I wrote down something like that. But then in a later lecture, I wrote down the same dipole-dipole coupling Hamiltonian in a very different way. As the product of the second rank tensor written in the laboratory frame with the spin tensor written in the laboratory frame. That was actually after the secular approximation. So one thing which I didn't cover, and it's I think quite an important subject, is how on earth does this correspond to this? They look very different. And the same goes for the other spin Hamiltonians. So what this is about is what one's writing here is, this is called a second rank Cartesian tensor. In other words, x, y, z. So this one, the elements here we would call djk, xx, djk, yy, xy, and so on. 9 of them. Well, these things here are called second rank spherical tensors. And I showed a tried to show how one transforms the second rank spherical tensors between different reference frames using Wigner matrices. Now I could have done exactly all of the mathematics using second rank Cartesian tensors instead. The results would be the same. But the spherical tensors actually give a more uniform machinery for doing these sorts of transformations. But it's worth saying something about the correspondence between these two forms. And then the second point, which Gabriella just pointed out, which is a very valid one, is that really this is after the secular approximation. And I should say something about what that is and why it works, or under which circumstances at least. So if I call this the full dipole-dipole coupling Hamiltonian before the secular approximation, I should write that down. So let me write it down actually. It's actually a sum over, since we're talking about second rank interactions, it would be a sum over 5 terms, with m going from -2 to 2. And the way it works is you take the corresponding space parts, you have to take the adjoint. I'll talk in a minute what that's about. Multiplied by the corresponding spin terms. So the second rank tensors, we have 5 spin operators with m going from -2 to +2, and 5 components of the second rank spatial tensor with m going from -2 to +2. And you simply take the product of them all. Just with this slightly tricky adjoint thing, which works as follows. That if you take the adjoint of a tensor, a spherical tensor, you always get minus the component with the negative value of m. So you get minus if m is odd, and plus if m is even. That's just the way spherical tensors work. So this is an example actually of taking 2 tensors and combining them. In this case, the particular combination which is being used here is a way to combine them to make a scalar. So this full Hamiltonian here is a scalar. Scalar means rank 0. And again, I'd like to use this picture here in which we have rank 2 being combined with another rank 2 to give an object which is rank 0. So this is the mathematics of spherical tensors actually, how to take 2 spherical tensors and make combinations of them to make a rank 0 object. So then that's called a scalar product. It's very similar to when you have 2 vectors and then you do this thing. That's called a scalar product of two vectors. And the answer is a number which is invariant to rotations. It's a scalar. So if you take the scalar product, you have two vectors. The scalar product of the two vectors is independent if you rotate the two vectors. So if you give this vector a rotation down here, and you give this vector the same rotation, then the scalar product of V1, V2, which depends just on the angle between them and the length of the vectors, is the same if you rotated the vectors. Which is why it's called a scalar product. It generates a number, something which doesn't depend on rotations. So that would be a scalar product of vectors. This scalar product of irreducible spherical tensors if they have rank L, takes the basically sums pairwise all of the components of the two tensors, very similar to the vector product, which is defined just by taking the sum pairwise of the Cartesian components and adding them together. You can see this generates a very similar type of object. It would be AL minus L adjoint TL L plus AL minus L plus 1 adjoint TL, minus L plus 1, and so on. If the second rank tensors, there are 5 terms. So the Hamiltonian which comes out of this is a scalar. It's independent of the reference frame. And it must be actually all Hamiltonians in the most, before you start to make approximations, they have to be scalars. They have to be independent of the reference frame. That's basically relativity. So in fact, in this case, the spin Hamiltonian, or Hamiltonian, any Hamiltonian actually, has to be invariant of rotating everything. And that corresponds to the conservation of angular momentum. So this links into the conservation of angular momentum. So another way of saying this is the invariance of the Hamiltonian to rotations as a consequence of that, angular momentum is conserved, which is one of the most important conservation laws in physics. incidentally, if you want to know where this link comes from, there was a German scientist called Noether, who was one of the few female physicists developing fundamentals of quantum theory, and in my opinion a bit underappreciated, maybe because of that. So it's a very important, beautiful result. It applies actually to many different operations, not just angular momentum. But this is the important one here. So the full form of the dipolar Hamiltonian between two spins is actually the scalar product of the space and the spin tensor. And it's invariant to rotations. So these terms here, the actual form of them, they can be written in different reference frames. So just as I've written here, I said explicitly, this has to be in the lab frame here. So I could say lab frame here and lab frame here. I could say molecular frame here and molecular frame there. I could say principal axis frame here, principal axis frame there. It wouldn't matter. I get the same result in any case because it's a scalar product. So actually this equation, the scalar product of the two tensors, is a sort of general starting point for spin Hamiltonians, actually. And actually when one does, we're not doing it here, but if one wants to develop relaxation theory, then actually you have to start with this equation and then take it off through all sorts of perturbation theories to get the relaxation superoperator. Which is usually called big gamma. So some of us in the group work on the relaxation theory of molecules in solution, in particular long-lived states. And for that we have to take this route. But what we're talking about at the moment is actually a little bit of a simpler topic, which is essentially that we have two spins which interact with each other. And then we apply to that a whopping great magnetic field. So the Hamiltonian, okay, so let's imagine now we have those two terms in the Hamiltonian. So I have the Zeeman interaction, which involves the spin system interacting with the large magnetic field. And I have the dipole-dipole coupling. I start with the full form of the interaction, not after the secular approximation. let's draw up that little table again. So we have space, spin, field. And we have two terms here. We have the Zeeman and we have the dipole. So which numbers do you remember, do I put into that table? Anyone want to give me some?
Space.
Sorry?
Dipole is 2 space.
Good, yeah. More?
It's 1 space.
No.
2.
2. That's why I have 2 here.
Oh, yeah.
Okay, you're thinking of CSA, which we can add as well. So CSA is 2 for spin, 2 for space, 1 for spin. What about the field part of dipole? Sorry? 0. Yeah, it doesn't involve the external field at all. It's just the 2 spins see each other, don't care about anything else. What about the Zeeman interaction?
Is that 1?
Yeah, 1 for what?
2.
Yeah, good. What about the others?
0.
0 for spin.
No. 0 for space. Remember, space is, when we say space here, what we're talking about is the rotation of the molecule. Well, the Zeeman interaction is an interaction between the nucleus, the spin, and the external field. The molecular environment is not involved in that, actually. The way it does come in eventually is through the chemical shift, but that's a sort of different interaction. What about spin part?
Is it 1? Is it?
1, yeah. That's right. And then CSA?
0.
No, it's 1. So it does involve the field. The CSA is the most complicated interaction. It involves actually all 3. All 3 terms.
What is it that dictates the rank of these, whether they're 0, 1 or 2?
Well, in a way, you could say that the numbers here define the interaction. And you could say from this, okay, some interaction which depends on the rank 1 part of the spin interacting with the rank 1 part of the field. And then the next question is, does such an interaction physically exist? And then if you find it, you give it a name. Well, you find it does physically exist, and it turns out to be called the Zeeman interaction. So you could, in a way, it's sort of backwards. And it's really quite possible you could say, well, is there an interaction which is rank 2 for the space, rank 2 for spin, and 1 for field, for example? Well, actually, I don't know of such an interaction, but theoretically, it's quite possible. It's just that when you do experiments and then you explain the experimental results using different interactions, at some point, for a start, you find out that you don't need anything more. Everything which is observed has a name for it. And then if you do quantum theory, you can actually derive the size of these interactions, and you find that such interactions could in principle exist, but they're incredibly small. So,
But in principle, you should have a scalar if you multiply space, spin, and field.
you have, that's correct. When you combine these angular momenta together, you have to get rank 0. But the way you combine angular momenta is, well, the way it goes is that if you have if you have angular momentum L1, well, okay, suppose you have angular momentum L1 and angular momentum L2, you can combine them in such a way that you can get total angular momentum anywhere between the difference and the sum. So, for example, this is a very important property here. Combining angular momentum. So, for example, suppose you have spin is a type of angular momentum. Suppose you have two spin states, and two spins, they both spin a half. You can combine them to get a total spin equal to the difference. A half minus a half is 0. Or the sum, half plus a half is 1. And there's nothing else in between. You have to go in each steps of 1. So those are only two possible combinations of two spins a half. And yeah, these exist in reality. This is called a singlet state, and this is called a triplet state. So that's one example of combining angular momentum. So let's say look at this one, the CSA. So basically you can combine 2 for space, 2 for spin. They can combine to give either the difference, 2 minus 1 is 1, 2 plus 1 is 3, or anything in between. So they can also combine to give 2 as well. So there are 3 ways of combining angular momentum 1 with angular momentum 2.
So now, when you're talking about that there, are you talking about physical, so quantized values of angular momentum, or are you talking about the rank of an interaction?
Well, actually, they behave in just the same way. So these spherical ranks obey the same mathematics as angular momentum. So yeah, I use those words interchangeably, actually. So these numbers here, which are spherical ranks, you can think of them as angular momentum. They have the same mathematics. So the 2 and 1 can combine to give 1, 2, or 3. And then they can combine, each of those can now combine with the field, which is another rank 1. So this could be combined with 1 to give 3 minus 1 is 2. 3 plus 1 is 4. So this can combine to give 2, 3, or 4. 2 can combine with 1 to give 1, 2, or 3. And 1 can combine with 1 to give 0, 1, or 2. Well, the crucial thing is, though, is that in amongst all of this big mess, we have a 0. The combination of all these all together to be a Hamiltonian has to be 0. So that just simply tells us that it's legally possible to combine rank 2 space, rank 1 spin, rank 1 field, to get something which is overall rank 0, which is a Hamiltonian. So that says that these numbers, 2, 1, 1, can in principle be a Hamiltonian. Then it's up to the physics to decide, is that Hamiltonian actually found in nature? And in this case it is, it's called chemical shift anisotropy. But there still may be some Hamiltonian terms which are perfectly legal, but which at the moment have never been observed. They're either too small to observe, or nobody's done the right experiment yet. And occasionally we see effects which we usually speculate widely as some new terms nobody's seen before. And it always turns out that we just did the experiment wrong, or we didn't understand it right. So far the only terms for almost all NMR, you don't need anything more than these terms which we're sketching out now.
For example, an interaction which is 1, 1, 1 in space being field would be in principle possible.
It's possible and it exists. And that brings me to the next topic. And in fact, your experiments, Gabriella, even involve it. That one is called the antisymmetric chemical shift. This is a very obscure interaction. But it turns out actually that in the relaxation of long-lived states, this interaction actually turns out to be quite significant. But for most of the 99% of the NMR world, you just totally forget about it. It's insignificant. If we're talking about obscure interactions, then one which we didn't talk about yet really is the quadrupole interaction, the electric quadrupole. This is for spins larger than 1/2. And it's an electric interaction, all the other ones are magnetic. And this actually has exactly the same symmetry as the dipole-dipole interaction, 2, 2, 0. So deuterium spin 1, nitrogen 14 spin 1, sodium 23 spin 3/2, and so on. They all have this electric quadrupole interaction. Then you can even have, so we're getting into obscure territory now. There's even a 3, 3, 0, an obscure one. And actually, no, that's the magnetic optopole. Yeah, this would be called a magnetic optopole interaction. And then even more obscure is 440, which is called the electric hexadecapole.
What makes one magnetic and the other electric?
Yeah, so, okay, we're in obscure territory here. But, no, I shouldn't have gone into this, but if you think about the nucleus, okay, the nucleus is a collection of protons and neutrons. So it has a charge distribution which is actually not necessarily spherical. it's like a potato, basically. And the way one treats that mathematically is to treat it as the sum of spherical harmonics, which look just like orbitals again. Well, whatever. So you can maybe imagine that any arbitrary irregular shaped object could be expressed as a sum of many different multipoles, these are called. So this is called a multipole expansion. So for example,
interaction with the transition methods and the correct transition method to classify.
yes, but that would be the electronic states. So here we're actually talking about the nucleus. So we have, so suppose we have an atom of cesium, isotope 133, so it's got 133 protons and neutrons together in the nucleus. And then it's got a bunch of electrons going around as well. Here we're talking about the nucleus. And in general, the nucleus is not like, you picture it usually as a round ball, but that's actually not generally accurate. And in fact, if you read about high energy physics experiments, they even construct nuclei which have like dumbbell shapes and crazy geometries of the nucleus. Now what one usually does though is expand the charge distribution, so you have a positive charge. You assume it's uniform to first approximation, so it's like a sphere. But then you start adding extra terms on it. So this would be so we'd have a spherical distribution of charge, and then it would have an electric dipole moment, just like a molecule can have an electric dipole moment if it's sort of HF or something. Well, a nucleus can also have an electric dipole moment, except it can't. It can, but it can't, because at least according to the standard model of nuclear physics, which is one of the best sort of theories of nuclear physics interactions, but not a perfect model. There are deviations that have been found from it. But within the standard model of nuclear physics, which was developed in the 1960s and 1970s, one of the results of that is that a nucleus cannot have an electric dipole moment. And in addition, an electron can't have an electric dipole moment either, for example. Now, the standard model of nuclear physics might be wrong, or it might be some deviations observed. One of the ways one could think of trying to detect that is to try and do NMR experiments where you find some evidence that a nucleus has an electric dipole moment. Oh God, I've gone off in really such a tangent here. But it's an interesting topic. Anyway, so you can't have an electric dipole moment. What you can have, though, is a magnetic dipole moment. And of course you do, that's what NMR is based on. So you have a magnetic dipole. You can't have an electric dipole, but you can have an electric quadrupole. That sort of quadrupole means basically that you have 4 charges which are arranged in that geometry.
Why have you put the magnetic dipole on the S orbital, not the P?
Yeah, so the reason okay. Okay, the way it goes like, you ask such awkward questions, Mike. Okay, I'm going to make a table of spin, nuclear spin. Start with 0, 1/2, 1, 3/2, 2, 5/2, and so on. And then the possible moments which some fundamental theorems of nuclear physics, which I don't understand, I only know the results, provide. So this is just what I know, but at least I think I know. So if you think of the types of moments, it turns out that you can have are magnetic dipole, electric quadrupole, that's this type of thing, magnetic octopole, that's somehow, and I don't know how to draw that, that's somehow like 4 bar magnets arranged somehow. So 8 poles. So this is north-south, right? Somehow we're going to have north-south, north-south, south-north, south-north. Somehow. And then electric hexadecapole. Hexadecapole means 16 poles. So we have to have, well, 8 pluses and 8 minuses arranged in some symmetrical pattern. Well, the way it works is that if you have nuclear spin 0, you can't have any of them. So it means that carbon-12 nucleus, for example, which has nuclear spin 0, is completely spherical. Even though it has 6 protons and 6 neutrons, somehow the wave function is completely spherical. And it doesn't have a magnetic dipole moment, and it doesn't have any of the electric moments either. Spin half, though, can have magnetic dipole moment, but it can't have any of the others. And actually that's why NMR concentrates, for the most part, on spin half nuclei, because they have this very, very simple interaction with external magnetic field, only through the magnetic dipole moment. Spin 1 can have magnetic dipole and electric quadrupole. So if you have spin 1, then you can have this interaction. So this corresponds, the electric quadrupole corresponds to the rank 2 interaction. And then you guess maybe how this works out. So if you have spin 2, spin 3 halves, like say sodium 23, you have magnetic dipole, that gives you NMR. You have electric quadrupole, that gives you the electric quadrupole interactions which influence the NMR spectrum of sodium. And in principle, you can also have a magnetic octopole interaction as well, which is actually rank 3. So that's this one. But just because something is allowed doesn't mean to say that it's detectable. And I think there have been some experiments where this type of interaction has been detected, although not for sodium. And similarly for rank spin 2, which actually there aren't any nuclei, in principle though you could have the electric hexadecapole and so on. So the standard model of nuclear physics, which is very good, one of the results is this table. And it tells you that spin half nuclei can only have magnetic dipole interaction. That's the basis of NMR. Spin 1, you can also have the electric quadrupole, and that's the basis of quadrupole effects in the NMR of spins larger than 1 half. And it just happens that for the nuclei which people care about, these higher interactions are extremely small, very hard to detect, and of no consequence whatsoever, which is makes me wonder why I spent half an hour of my life talking about them. You never know, maybe one day they will turn out to be useful. Actually, it reminds me actually of, I once visited the lab of a good friend of mine called Jerry Harbison in America. He likes these obscure things. And he had a nice poster on his office, which I like, which was a very complicated NMR experiment, which was detecting the electric hexadecapole moment of iodine or something like that. And then at the end of the discussion, they sort of decided that the electric hexadecapole moment of iodine from the experiments was undetectable and was less than a certain quantity. And at the end of the poster it said, "Your tax dollars well spent." Yeah, so but maybe one learns something from just the way the theory develops. It sort of gives you a feel about what these things can be. So let's just scrub those off. Actually, it times out anyway, pretty much. But okay, so if Michael doesn't ask any more questions, then I can proceed. Yeah, so those are, what are we doing? Those are interactions, yeah. So they have to be rank 0 altogether, overall, when you rotate everything. Now, the Zeeman interaction is the interaction between each of these two spins with the external field. And now, since the field is applied in a certain direction, that imposes a certain direction on the interactions. So the Zeeman interaction, so if we imagine the Zeeman interaction between a spin and the magnetic field, it has to be a scalar. It has to be independent of rotations. And this would mean the rotations of the whole system. In which the magnetic field is rotated as well as the molecules and the spins. That's the sense in which the Zeeman interaction is a scalar. So basically, if the Zeeman interaction is independent of rotating laboratory, including the magnetic field, including the spectrometer, which is actually what happens all the time, because remember, we're on an Earth which is constantly rotating. So if you do an experiment 12 hours later, the magnetic field direction has changed because the Earth has gone around, right? So if this wasn't true, then the NMR spectrum would change. as the Earth rotates. But in fact, because the Hamiltonian is a scalar, then it doesn't matter. So the interaction, the Zeeman interaction, actually has this form: minus gamma I dot B. So the scalar product of the spin interactions and the magnetic field. And the dipole-dipole coupling is also scalar, giving us this scalar product of the rank 2 interaction. I'm going to use a slightly fancy notation for it. That's a fancy notation for this scalar product here. Basically take two rank 2 tensors, combine them and take the rank 0 part. So two scalar products. And we can expand this out. So now we take a particular case though. Now we say that B is the magnetic field along the z-axis. So then this is minus gamma B0 IZ. And which Z are we talking about there? The Z is the axis system in which the Z-axis of that particular frame is along the magnetic field. That's the definition of the laboratory frame. So this spin operator here is explicitly or implicitly defined in the laboratory frame. This scalar product here can be defined in any frame. It's invariant to rotation. But if it can be defined in any frame, we might as well choose the laboratory frame for that as well. So that's actually the full form of the spin Hamiltonian, including the Zeeman interaction and a general dipole-dipole coupling. This is where the secular approximation comes in. Actually, this is really a matter of perturbation theory. Oh dear, that's another topic. Perturbation theory. Perturbation theory is typically you have two Hamiltonians. You have a large one and you have a small one. And in first order perturbation theory, you simply determine which parts of the small one can you safely neglect because of the presence of the large one. And the way it goes is you I'm getting into, I think this is actually. I think to do this properly, I think I have to reserve another time. So let's see, I have this other lecture going on. Monday morning. Would anyone like me to continue Monday morning, same time?
Yeah.
Yeah? Okay.
Can I have a little bit from the lecture with you, please?
Okay, well, I like chocolates. Okay, just a hint. Okay, I tell you what, we'll continue. I'll continue on this next week after my other lecture. Because to really explain that sector approximation, I think we really have to start talking about perturbation theory. I hadn't realised actually. Yeah. Okay.